Okay, Matt Roscoe here at the University of Montana, section 3.2, derivative formulas for the exponential and logarithmic functions. So I'd like to do a quick Desmos exploration of a to the x and then talk about the derivative formulas for e to the x and a to the x and e to the kx. And then we'll do another Desmos exploration of ln x, or the natural log of x, and then formalize that in a rule for the derivative. And then we'll go through 4 or 5 examples. So let's get right to it. Take a look at a Desmos exploration. So here we have a function of the form a to the x, and we have a point on the function that's controllable by this slider, the second slider. So the point on the function, but of course a to the x is also controllable. We have all kinds of exponential functions with bases greater than 1, which would be increasing exponential functions, and then if you have a base less than 1, of course we get a decreasing exponential function or an exponential decay function there. So let's leave it right now at 1.74 and then talk about the derivative of, let's maybe make it a little bit higher. How about 2? So let's talk about 2 to the x and look at its derivative. So if I take a look at how the point on the graph is, the slope of the point on the graph is changing, it should give us some intuition about the derivative. So I can see that the slope is positively valued, but very close to 0 when I'm back here at negative values of x. And as I move forward, it's positively valued and growing steeply, growing quickly. So it appears that it is a positive everywhere type of derivative. If I put in a point that indicates the actual value of the slope, then I can see that the slope is closely mirroring the graph back here, but then it breaks away, but is also growing. So that's the path of the derivative, or the value of the slope of the function at any point on the graph. And the question now becomes, well, what is that derivative, right? What's the algebraic representation of that derivative? So let's just leave the graph and its derivative drawn at this point, and we'll take a stab at it. And right away, what I think is that it looks a lot like an exponential function. So let's start out with a to the x. But let's put something in front of it that dilates it. So we'll put a k in front of it, and then add a slider for k and see if we can get some intuition from that. And I can see that now I have an exponential function with a dilator, that allows me to try to sort of get a sense of, well, what is that black function? And so when I push it back, I can see that it's about 0.17. I'm going to change this step from 0 to, I don't know, 2 and step it by hundredths. And just see if we can get a little better estimate. So somewhere in that neighborhood. 0.69. And if we write that down, let's go ahead and get some things written down. So when f of x is equal to 2 to the x, then f prime of x appears to be equal to 2 to the x times 0. Somewhere in the neighborhood of 69. Let's bump it up and see if we can play this game again. If we move f of x to 3, the base to 3, what do we get there? So moving my, I'd probably zoom in a little bit closer here. Moving my derivative function's value of k close here to, it looks like it's somewhere in the neighborhood of 1.1. So if I have something in the neighborhood of 3x, I get 3x times 1.1. Let's see, let's move it to 4x. And in that case, k is going to increase to somewhere in the neighborhood of 1.38. Well, let's just go one more step here, run it all the way up to 5, and ask what k would have to be. Somewhere in the neighborhood of 1.62. And so the question is, if we want an algebraic definition of what the derivative is, we can see that one way we might write it is by just saying it's another exponential function with the same base with some k value, but we'd really like to know what function is governing that k value, right? We can't just say it's some k undetermined. So one thing I do notice that might be interesting to pursue is something interesting is going on in between here and here. Between 2 and 3, I can see that k value goes through 1. So it goes from 0.69 to 1.1. So if I could figure out for what value of a over here, or what base value, so what to the x equals that same what to the x times 1, then that might give me some intuition about what function is happening in there. So let's go ahead and see if we can figure that out. So it's somewhere between 2 and 3, we know. So what am I looking for? I'm looking for the spot where that derivative graph matches the graph of the function itself, and it seems to be really close to 2.7. I'll go ahead and change it. I'll step it from 2.7 to 2.8 by 0.1s. See if that'll help us. So I can see it's above there and below there. So it looks like let's zoom in a little bit more. It's below, and above or right on, somewhere in there, 2.71, 2.72. So let's put 2.71 in and run it to 2.72 by 0.1s. Okay, so let's see if we can get a sense of, now you can just barely see it moving, but if we zoom in, we should be able to get a better sense of what's going on. So definitely above the graph at this point at 2.72, below the graph at 2.71, I see. Okay, so now I'm seeing something really close. Well, somewhere in there, 2.7182 seems to be roughly where the graph is equal to its derivative, the base on the exponential function. 2.7182 is equal to 2.7182. But of course, we know that we could keep zooming in, and this seems like it's a rough estimate at this point. But what you should notice is that this actually turns out to be this very special number, e. E is equal to 2.718 dot dot dot. It's an irrational number, and it does have as itself its own derivative. So we've discovered that. But it also gives us some intuition about how we might know what these things are. Now, it makes good sense that that this multiplier depends on the base, so it should be some function of 2, 3, 4, and 5, right? And what we're really looking for is the one who, when applied to e, gives you a 1. So what function, when applied to e, gives you a multiplier of 1? Well, none other than the logarithm function. It undoes the exponential function, so it gives you back a 1. So that's the idea here, is that we would guess that this is e to the, the natural log of each of these, and a quick check will allow us to see, is indeed the natural log of 2 equal to that? Let's try it. It is about 0.69. Is the natural log of 3 Yeah, it's about 1.1, and the natural log of 4 is about 1.38, and the natural log of 5 is about 1.61, so we got a little measurement error over there. But in general, what it appears to be happening here is that if you have something of the form a to the x, then its derivative would be still a to the x times the natural log of a. So let's go back to our slides and take a look here. So the derivative of e to the x we found out is just e to the x, and the derivative of a to the x is a to the x times the natural log of a. So this would be like your vertical scaling of the exponential function that results when you take the derivative. It turns out that you can now apply this to another setting. You can take a look at what happens when you have e to the kx. So let's take a look at that. So if I have something of the form e to the kx, how can I deal with it? This, by the way, is a real common form of the exponential function used in science. So let's think about, first, before we proceed, since we don't know what to do with that, let's think about how we could think about it. We can think of e to the kx as e to the k raised to the x, right? And now, think of this thing as simply a number, right? It's e, which is 2.71 dot dot dot, raised to k, which is some constant, so some number. So this thing can be thought of as sort of like an a. So it's sort of like an a to the x. Well, we know how to deal with a to the x. We know, if f of x is equal to a to the x, then f prime of x is equal to a to the x times the natural log of a, right? So if that's the case, then we should be able to apply that rule to find the derivative of the black function up there. We can say that it's just a to the x, which in this case is e to the k to the x, right? A to the x, where a is e to the k, times the natural log of a, where a is e to the k. And now I notice that, well, the natural log of the exponential function, those two are inverses, so they undo each other. So this guy is just a k. And over here, e to the k to the x, well, that's e to the kx, the same as what we wrote up above. So the derivative of the function of form e to the kx must be k times e to the kx. So the k comes out in front whenever we take the derivative of something that has an argument next to the x value. So we just found that the derivative of e to the kx is k times e to the kx, where k is a constant. Let's take a look at the natural log now. The natural logarithm function should be familiar to you. It looks like this. It has a restricted domain from 0 to infinity. If we put a point on that function, we can kind of think about how the derivative should look. And the derivative appears to be positively valued, very steep at the beginning, so it would be very highly positively valued, but then that positive slope is decreasing as x increases, so it starts very high and then decreases to almost 0 by the time we're out at 6. It's pretty small, but if we move it back to, say, 1, it's valued there. If we move it to a half, it's valued there around 2, and extremely high here. And if we put in a picture of what that looks like, then the dotted line is the derivative of the red function, which is the natural log function. So just like the natural log function is monotonically increasing, so it's increasing always, the derivative function seems to be monotonically decreasing, so it's going down in value as that function gets flatter and flatter. So that's a good picture of what we have going on here. Let's go ahead and get rid of a few things and then talk about, well, what is the function here? And it might be most intuitive just to look at values of the function. So here at 1/2, I can see it's, if x is 1/2, it's 2. When x is 1, we're in the neighborhood of 1. When x is, say, 2, we're in the neighborhood of a half. When x is 3, we're in the neighborhood of a third. When x is 4, we're in the neighborhood of a quarter. Well, that makes good sense now. When x is 5, we should be a fifth, and indeed it's about 0.2. And so it appears to me that the derivative of this function is quite easily found by looking at values. I think it's just 1 over x, right? Yes, and sure enough it is. So the derivative of the natural log turns out to be 1 over x. I should say that all of these rules can be more formally derived using limits, and that information is available to you if you're so inclined at the end of your chapter. Let's take a look at a few examples now and work through some of those. I'll put us in split screen mode and we'll try them. Okay. So the first one we're going to do is x squared minus e to the x. So what's f prime of x going to be? Well, that'll be the differential operator applied to the right-hand side, which is the same thing as the differential operator applied to the difference, each term in the difference. This is a power rule, so it'd be 2 times x and minus, this is an e to the x, so the derivative of e to the x is just e to the x. Okay. So let's take a look at the next one. What if we were to just change one little thing here, call f of x x squared minus e to the 2x. We put a 2 there instead of a 1 up here. What does that have? What effect does that have on the derivative? Let's find out. Well, I can see right away that we're going to get something really similar. I'm going to skip to the second step here, apply the differential operator to both pieces of the difference. I'm going to see that this is again a power rule, so 2 times x minus, and here we have something of the form e to the kx, whose derivative is k, which is 2 here, times e to the kx. And so generally that's our derivative. We could also write it in factored form if you wanted to, x minus e to the 2x. So a little different here. 2x minus e to the x, 2x minus 2 e to the 2x. Of course, the 2 seems to have propagated both out in front and then stayed up in the exponent as well in the derivative. Let's try a new one. How about this? 3x minus 2 times 4 to the x. What is the derivative there? Well, it's d by dx of 3x minus d by dx of 2 times 4 to the x. Sorry, I'm running out of room there. So we've got a constant multiplier on both of these. I'll take it out in front. 2 comes out in front times d by dx of 4 to the x. Okay, so now we take the derivative of x to the first, which is just going to be 1. As 1 comes out in front, we kind of think of x having an exponent of 1, so the 1 comes out in front. We take 1 away from the exponent, that's 0. So anything to the 0 is 1. 2 times, now we have an a to the x form. We know the derivative of a to the x is just simply a to the x times the natural log of a. And now we have to clean this up. 3 times 1 is just 3, minus 2 times the natural log of 4 times 4 to the x. So that would be a perfectly acceptable way to leave it. Let's try one more example. 2 to the x plus ln x. So what's the derivative there? So that would be the derivative applied to 2 to the x plus the differential operator applied to ln x. The derivative of 2 to the x is 2 to the x times the natural log of 2. And the derivative of ln x is 1 over x. And sometimes we like to write the coefficient out in front, so the natural log of 2 times 2 to the x plus 1 over x is our answer there. Okay, let's move on and take a look at an applied problem. So it says that the value of a car purchased in 2007 can be modeled with this equation, where t is the time in the years since 2007, and v of t is the value of the car in thousands of dollars. We're supposed to evaluate and interpret v9. So number one, what would be v evaluated at 9? Well, that's easy enough. We just plug in 9 into our function. So 25 times 0.85 raised to the 9th. So we get 5.79-ish. So how do we interpret that? We would say that in year, it's 2007 plus 9, or 2016, the car, not care, is valued at 5.79 thousands of dollars, so what, $5,790. I should probably put about someplace in there, but I think that's good enough for our purposes here. Number two, we're supposed to find the derivative with respect to t. So v prime of t is going to be the derivative with respect to t. We're just swapping variables here, no x, just a t. 25 times 0.85 to the t. Okay, constant multiplier, we can bring that out in front. 25 times d by dt of 0.85 raised to the t. This is an a to the x sort of formula setting, so we can use that derivative of a to the x here. So it would be 0.85 raised to the t times the natural log of 0.85. And probably should put those out in front. 25 times the natural log of 0.85 times 0.85 raised to the t would be a perfectly acceptable way to leave it. And let's try to find v prime of 9. So what would be v prime of 9? Well, that's easy enough. We just put 9 into this formula above. So it'd be 25 times the natural log of 0.85 in parentheses times 0.85 raised to the 9th. Negative 9, let's see, negative 0.941. Now that we just have to contextualize that. So let's think a little bit about what's going on here. You know, we've got this formula that tells us how v of t and t are related. We know that at year 0, if you look at the formula and put in year 0, you'll find out that it starts out at 25. This is dollars, but in thousands. Okay, dollars in thousands, and this is in years. And since the base on the exponential function is less than 1, we are reducing, so it's an exponential decay situation, something like this. And what we found so far is we found that at 9, year 9, if we go up here, it's predicting a value of 5.79. So $5,790 in year 9, and then we've just calculated the slope at that point, and that slope is negative 0.941 in value. So it's telling us the rate at which the car is depreciating in year 9 in thousands of dollars per year. That's one way we could make sense of interpreting that number. So let's go ahead and write that down. In 2016, which is year 9, after 2007, right? The car is losing value at a rate of what is it, 941? It's thousands of dollars, so $941 per year. Okay, that's about all I wanted to show you today about the derivatives of the exponential and logarithmic functions. Let me know if you have questions.